Hello, everyone, and welcome to the fifth chapter of Introducing Python. This chapter is about functions and object-oriented programming. It's thankfully, I think, considerably shorter than the last chapter, but it's pretty tricky as a chapter. These are really some complex concepts, and they're ones that, certainly for myself, I didn't quite get at first. And object-oriented, I didn't quite figure it out. I trained in Java rather than Python, but at one point I had kind of an aha moment as to why they're useful and how they're useful. And I feel like a lot of people get that aha moment with these things. I hope this lecture can maybe provide some of those, some scaffolding to help you get those moments as well. But the important thing about it is that there'll be really useful skills for navigating through Python. This will be, I guess, the last of the kind of the key core skills for Python itself. And the next chapter, we will be looking at things like how to do Python with a script, how to write files, how to read files, and kind of go beyond JupyterLab. But once you clear through here, you're really well on your way to being able to use Python in a flexible way for a variety of circumstances. Whether, like myself, it's more towards the social sciences, or whether it's towards just straight up programming and computer sciences, or any other sort of ways in which you might apply Python in your own work. So yeah, to give us a sense of where we're going here today, first functions and object-oriented programming. We're going to define a function, and then we're going to talk about scope. So what's inside the function, what's outside the function, how do those two play nicely? We're going to look at the different ways in which you get stuff into the function itself, or ways of passing data into a function. And then think about how we get stuff back out of it, how a function returns data. Now, then we're going to go on and I'm going to show some classes. And classes are examples of ways in which we can create objects. And so once we have a notion of an object, then we're going to be able to do things like a function, except it's going to be called something different. It's going to be called a method. And so we'll see how methods work with classes. And then we'll see how to create our own, how to extend other classes, and then some reasons to use them. I'll talk through that with an example. I think about creating receipts for a store. And then we'll conclude. So to begin, to remind, as usual, restart kernel and clear all outputs. You can have a copy of those outputs yourself to check up later, but for the version you're working with, we're going to want to clear all that so that we can see things as they unfold. Okay. And of course, you can also launch this on Colab or on Binder, but I am, as usual, using JupyterLab. So why do we do this? Well, functions, as I say here, they allow you to group together related operations in a way that can abstract details away in your program. So two main use cases of functions come to mind. One is to avoid repetition and the bugs that can come from inconsistent code. So when we say we abstract away the details, we kind of figure out the same thing to do. Imagine like a morning ritual, and you always will kind of go to the morning ritual function to kind of like, when leaving the house, do you have your keys, do you have your wallet, and so forth and so forth. So once you put that in one place, you don't need to write a new checklist for that for every day. Now, that doesn't mean you wouldn't need a different checklist or a slightly different checklist depending on the day, but that's how we determine which things we want to put into a function, which things we want to put into a function using some conditions, and which things are part of the program itself. And yeah, we all want to group together operations that are used elsewhere. So for example, when we use list comprehensions, it's really tricky to put multiple things inside a list comprehension as transformations of a variable. So if we have a list and say it's 4 names, Alice, Barb, Cam, and Diane, whatever, and you want to turn them all into uppercase, well, that's easy. It's, string.upper. But what if it's not just a name that you want to turn to upper, but it's maybe a large piece of text, and you want to do something for every large piece of text? Maybe you want to split it into sentences or check for certain words, and things can get pretty complicated. It's hard to do that in a list comprehension without making your code really busy. So you can take all those things that you want to do, those operations, put them in a function, and then call that every time you go through the loop or go through your list comprehension. So we'll see that, and hopefully it'll be a little more clear in practice. But we can see how we've already had some functions as well before, and why they can be useful with this kind of stylized example here. So we've seen functions such as print and len, and in these cases, to remind, the function name is, in this case, print, or len. And these two parentheses afterwards, when you put them there, it's a way of suggesting that the program will run. So, for example, if I go print, let's say we have a list that's, it's got 3 elements in it, and we print len ll, it should print 3. Okay. Now, if we printed just len itself, it should say, yeah, it's a built-in function. So this right here is the function, and when you put the 2 parentheses afterwards, it runs that function. And how does it run? Well, it takes whatever's inside those parentheses, passes it to the function, and then this entirety stands in for, represents the output of that function. So to kind of get a sense of this this example here, I just want to remind what modulus means. And that is the remainder of long division, or just the remainder of division, or integer division. So in this case, the remainder is 1. You divide 1001 by 1000, and you get almost 1. It's not quite 1. As we'll see here, it's probably like 99.99, or yes, the other way around. But it's not quite 1. There is, in fact, a little bit of a remainder. If we see that dividing in that way, we say, well, you get 1000 in there, but you don't get anything else. So that's the integer division, and this is the remainder. So, and while those were the same numbers, just to remind, see, that would be 3. And so we use the modulus in order to work as kind of a cheap iterator, or an iterator on the fly. So now let's see how we can use it down here. I say x equals 5 if x mod 2 equals 1. So what does that mean? That means if x is odd. So if x is odd, then what we'll do is we'll append to this list x times 2. So we'll make it even. Now down here, we see another one and say if x is odd, well, we'll append that to the list. Otherwise, we'll just append it in. Same thing right here. So this is pretty repetitive right here. Now, what we would have seen in the last chapter is that we would wrap this in a for loop. However, we can go a step further than that here and take that for loop and just put it somewhere else in the code. So just watch this. We have here, I wrote a function called double if odd. And it takes in a number as input and then says if the number mod 2 equals 1, just like up here. So if it's odd, then we'll double that number so that way it'll always be even. And otherwise return the number because it's already even. Now I said double if odd, I could have given it another name like make even, but this won't work now because it's called double if odd up there. But yeah, the name itself is not important, although it is useful to consider some conventions for that. One convention is trying to keep consistent with things like camel case versus hyphens. So in my functions, I am a little bit inconsistent, admittedly, but I often use camel case for my functions like this, double if odd, and you see those like so forth. Whereas some others, you'll see more like double if odd. But I tend to use that for variables, but that's just convention. But indeed, you should do that, and what you should avoid doing, however, is trying to clobber existing functions that are already in there. So what we shouldn't call this is len, because this will do something completely different from what the len function in the program is doing. And so then anytime afterwards, if you want to use len, it's going to use the version in the program and get entirely confused. So double if odd, I'm pretty sure there's no function out there called it, and it should work fine. So as we can see here, if we compare the output of these two, 5, 7, 12, and 15, we got 10, 14, 12, and 30. So the odd ones got doubled, the even one didn't. And same thing down here. But you'll notice what I've done in this case is because I wrapped it in a function here, we just call the function once within this list comprehension. And then these are the numbers we pass in. Yeah, we don't even really need to say like LL equals this. Oops. We don't need to say that and say for in LL. Remember, this actually represents, it stands in for. So we can kind of cut to the chase there and put that list directly inside the list comprehension. And then I'm just printing the result of it, and then we get. So now why would we do this rather than here? A couple reasons. The first, as I noted above, is minimizing mistakes. Imagine if you cut and you paste and you do something slightly different in one of them, or you change it, or you've got a typo. Uh, it's hard to know where, and it's really dangerous whenever you have multiple long strings of code that are very similar, and maybe it's just slightly different. So you copy this, you paste it elsewhere, and make a little change, but sometimes things can get out of sync, and you really want to make sure that you do the exact same operation every time. The other thing is, of course, it's all tucked away in the corner. So even if we do accurately, copy and paste this every time, I'm pretty sure that's an accurate copy right now, but it means that we just got longer code, and the code is harder to read. Maybe a little bit easier to read if you're not familiar, but as you get further on in code, you'll get used to having to zigzag in between functions in order to see what they do, or trace between functions to see what they do, and then think about what happens inside the function as having meaning. So now to build that function, we need four things that we have above. Well, we need a name, inputs, calculations, and outputs. So name, double if odd, inputs, num, and you can do something that doesn't have an input as well. But for a function, it tends not to make a lot of sense. There must be some sort of implied input, because a function is just kind of free floating out there in Python, waiting for input to return an output. And so the calculations, that's the stuff right here, and then the output is that number, or what is returned by the function. And you can see that's this green reserved word for return. Now here's a different function down here. It says double the number if even, so I've given it a different name. It says if num mod 2 equals 1. Now down here, if num mod 2 equals 0, return the input number. So I say double if even. Now, it's pretty similar as a function. Maybe we could even merge those in some way or another, or use other code snippets for it, but I wanted to just give you the sense of the parallel. Now you notice down here, we have a long set of numbers, and then we're going to get some new numbers out of it. And here we are, double if even. So 4 became 8, 6 became 12, but the odd one stayed the same. So that does pretty much what we expected it to do. And now if we just add new numbers, whatever, it doesn't really change significantly our code, how it's written, or this process right here, whereas indeed up above it would. So above, I talked about what we do inside the function, and just like with an if and an else statement, you can see visually we have indented in order to denote that we're inside the function. So this is inside, and these right here are outside. Now that's just a visual distinction. The conceptual one is it's all of this stuff inside here, because some programs or some other coding languages, they wouldn't necessarily use the indentation, but they would still have a notion of what's inside the function and what's not inside the function. So if things are not inside the function, then they persist before and after you run your function. But if they are inside the function, they get created, and when your function is done, your function forgets it. Now there's ways around that, more complicated ways. You can use a thing called yield, which is a more advanced technique. But for the standard stuff, what we're assuming here is that when we run this function, the things we create within it stay within it. So let's watch this right here. Multiply the value, got an input number. We got this variable x. X equals input number by 2. Value of x inside the function, return x. Okay, so it's just going to return a double of the number, and the rest of it is, all extra things that I've put in there for this illustration. Yeah, so value of x inside the function, x equals input number times 2, so it's 8. It returns that value, and then, so now here it becomes the output number. But the value of x outside remains unchanged. So this is the x that's inside. It was 8, and the x outside, 4, remains the same. Because x was not the argument, input number was. So what if we change input number inside the function? So when I run this down here, you'll see we took in input number, I doubled the input number, we printed that, so it's inside the function, it's 8. And then what happens when we try to print it outside the function? Well, it says right here, name error. Name input number is not defined. Now that's not an error. What it meant is that input number was sort of instantiated. We created an instance of it inside the function, but outside of the function, it doesn't really know much about what's going on there. So how might we go and affect that? Well, here's one way we can do it, and I don't recommend doing this, but I'm just using it to show the difference between inside and outside the function. So you see here we have this value x, and now I've called it global x. So above, if we just have x in here, modern versions of Python will throw an error, say unbound local error. You really gotta say what x is now. But if you put global in front of it, that's enough. That's enough for it to say that. And now just watch what happens with x. This actually then becomes the x even outside of the function. So x equals 4. So the value of x before, and here's the ID of it. So just watch. So that's what that variable is, and that's its ID in the memory. In fact, so the output number multiply the value. So we make it 8, and then print the value of x after the function ID x. All right. So look, this is a different ID. It refers to a different variable than the earlier one, and then x after the function actually ends up being the same one that's in here. So if we trace that again, this ID is referring to this x, multiply the value, so this happens then, which then prints this statement right here in this ID, a totally new value of x with a new memory register. But then when we get back down here, the value of x after the function, because it's global, it's actually the new internal variable, and we can prove that because it's actually got the memory address of the new variable, not the memory address of the old one. So global has kind of made itself global in that regard. Normally we wouldn't want to do that. What we want to do is just ensure that things stay within scope, and so it would be bad programming to kind of cheat through your functions, because then you can change variables all over the place and not know which change was the right one. That's the point behind keeping the variables within any function. Stuff goes in, stuff works around, stuff comes out. So I described it earlier as inputs, and I was, I guess, somewhat vague about that. But really what we're referring to when we talk about inputs for a function, we're talking about parameters. And parameters are these variables right here inside the function statement that suggest this is going to be something that we're going to use in the function. But we also have a notion of a thing called an argument. Oops. And an argument here is the value of a parameter. So a parameter, in this case, it doesn't really have a value. There's no default. We haven't assigned word to anything. So what value does it get? It gets big ideas here. So as we can see here, tiny examples, big ideas. What has happened is that this has become the argument passed in as input to the function. Okay, and you probably would have figured that out yourself so far with all the functions that we've used. But now let's just have a look at these in a little more depth. We can see here first what we're doing is we have just one argument here. I called it just name. So in this case, we just pass it in and it prints. It doesn't even return anything. It just does this stuff inside of the function. Now let's have a look down here. Here we have two additional arguments, or rather two additional parameters, and they're both set to true. I've called them setting 1 and setting 2. So if setting 1 is true, then we'll print the arg name. Else, if setting 2 is true, we'll print the arg name dot upper. Else, we'll say you have disabled the settings. Okay, so now we can think of a couple different ways we can combine these. Well, the first one, remember it's called example 2 here. So example 2, take 1. I send this in as the argument, and what's going to happen? Well, we haven't set in anything else, so it's going to use the defaults. It's going to say this is true and this is true because that's what the default values are here. So it says if setting 1 is true, which it is because it's the default, then we'll just print whatever the argument was. Now you'll notice here for the next one, I set setting 2 equals false. And is that going to change anything? We'll find out. I actually think it won't. So I'm going to liven it up and make setting 1 equal false. So now just watch here as I run this. Nothing's going to happen, or in fact, it's going to throw an error. It's going to say name error. Example 2 not found. And that's because Python doesn't know about this function until we run the code with the function in it. And it's important to remember that. If you do have functions that you use in your program, you might create a function, you're sort of working along, you say, oh, I need a function, I can put it all in here. Great. Just remember that wherever it is in the program, it has to be before it's used, because the program has to know about it. So let's run this. And now when we go down here, we should get some output. Okay. So in this case, set example 1, take 1, passed it in, worked just fine. And now in this one, the second one here, remember I said just make it a little more exciting, I said setting 1 equals false. So now this is false. Setting 2 is still true. So if setting 1, no, but that's false. Elif setting 2, that is still true. So we print name.upper, and that's exactly what happened. Now have a look down here. You notice I didn't say setting 1 or setting 2. So how does it know which one is the right one? And I think that's also worth pointing out up here. Well, if we run setting 2, it will work. It just doesn't really do anything exciting. But the thing about it is that setting these defaults, they don't have to. You can skip some. You can skip them along the way, as long as you do these ones here without a default first. And then as long as you have all them first, you can put these in any particular order. So in fact, I can also say setting 2 equals true, or perhaps say setting 2 equals false up top. Yeah, see, so for example, that they didn't have to be in any specific order, as long as they were after this. And you can try that out. We'll do that here. For example, if I throw this here at the beginning rather than at the end, that should throw an error. Positional argument follows keyword argument. So this is a positional argument that says we care about it because of the position it's in, because it's at the beginning. So that's how it knows. And then these ones right here, they have defaults. So it's okay if you don't set them, because there's already defaults available. All right, now let's have a look down here. Check this out. These are positional arguments are passed, but they're not defined ahead of time. So up here we had, one called argname, and then we had these other settings, and then we were able to work with those settings. Now down here, what if we passed arguments to a function, and we don't really know how many arguments ahead of time? We just want to keep it flexible. There's lots of reasons for that. I think one is you're just passing variables through the function, but regardless, you can do this. Here you see I have this one star, and it says args. Now that is actual code here. It doesn't have a color there, but the star there refers to this. Just says this is our positional arguments. So we have one here, and then we can have as many positional arguments as we like, as long as as long as we don't run out of memory. So in this case, I have one called some data, and then maybe, and then more data. Now it says here below, why doesn't it print some data? So let's just watch this. Any ideas why it doesn't print that? Well, you can pick through that function yourself in order to check that out. But to spoil some of the surprise, and that's because it's a positional argument here. So it says if len args is greater than 0, print those args. But this isn't in the args. This is a positional argument first, and then there's the rest of them. Yeah, and as figured, what's important is not the word args, although that is often what's used by convention. It's that this little star here says we're going to have some arguments after this. We're going to call them by this, and you can reference them by name or reference them by position, the first one and then the second one, and so forth. Now imagine if we, just like with data structures where we have lists, which is by position, we also have dictionaries, which is by association, and we have that as well for keywords. In fact, that's what the defaults were really. It's just it's like a dictionary entry with a key and a value. So imagine we have setting 1, setting 2. what if we have tons of settings and we don't really want to put them all in the function explicitly? Well, we can do that too, except we got 2 stars here, and then we say keyword arguments. Again, keyword args or kwargs here, that's also convention. You know, you can, I'll put a bunch of W's in there to show that it still works if we run it that way. What's important is that it's the set of arguments that starts with 2 stars. And you can kind of now get the parallel here. 1 star is like a global or an uncertain term, a wild card, if you will. And it's just for 1. So we have each one of these is coming in as 1. Now this is 2 asterisks because they're coming in as pairs of keys and values. And again, notice here that example, we didn't give that we didn't give that a keyword here. We didn't say, like, you know, ex equals. It's a positional argument, and so this should throw an error. Yeah, look at that. But if we wanted to keep it even, it is called just name. So we can say just name, but we don't need to because it's in the first position. But all the rest of them, because they're keyword arguments, we have to. If I do that, now it's expecting not key value pairs, but, you know, like a list. Oh, 1 argument after the other. So that should throw an error. And it's like, got an unexpected keyword, var1. It doesn't know what to do with it. Now finally, the last of these sorts of things that you can pass into a function that are worth attending to is the fact that functions are weakly cast like the rest of Python, which is to say it's not going to do checking of the type of variable coming in. Now that can be really handy. It says make double value. You know, maybe there's lots of things that we can double, or at least use asterisk and 2. And of course, so to remind, if we have a string, str, ex equals, or I probably should go like this, keep with convention, equals a, and print ex stir times 3, and so forth. So we could use that regardless of whether it was a string or whether it was a number. So maybe we want to have a kind of versatile function that doesn't check that. But we can also then get ourselves into some trouble here. So just look what happens. I say make double 2, and I guess that should return 4. I say make double double, and so that should return double double. And then if we say make double in this list, that should make a list with 2 entries in here that are both the string number 2. But what if we do this with a dictionary? Well, I haven't shown how to multiply a dictionary because it's not really possible. So I think that's going to create an error. Yeah, look at this. It did. It created a type error. Now in this case, I caught that type error. I understood that because this value is could be anything, sometimes it's going to be a problem. And so we wrap that in those try and except statements that we saw from the last chapter. To remind, errors to be handled and sometimes raised. You know, we get these errors. This is in the chapter 4 code. And then down below, you know, this try and except. And so here we see an example of that right here. Now, what happens if I don't do that? Well, of course, we can always try that out. And you'll see, yes, sure enough, that's the type error that we get. Unsupported type for this asterisk, dict and int. So whenever you create a function, it will return something, but that something might be nothing. So when I say that, and this gets back to some of that tricky stuff with nothings and not a numbers from a few chapters ago, yeah, it'll return the null character, or none, N-O-N-E. If you saw set down here when I wrote none, that was in this, it's a green word, which suggests it's one of these reserved systems words. Now that doesn't mean we don't have to see none for it to be the case, but it is there. And we can tell because now look what happens when I print this. I've called a function called no return, so we're past the point of no return. And here we are, we're going to pass in there. Now, why pass? Because we have to say something. If we do this, it just like, or for example, if we go def no ret, it will expect something more. It'll say, okay, where's the rest of the function? So incomplete input. Now, if you want to put some input in there just as a placeholder, you can say pass. And you can do that in lots of places. You can do that in an if and an else statement. So if something, and you don't really want to change anything, you can just say pass and then go else and do the things you want it to do. So in this case, we've done that down here. And now what's going to print? Is it going to print the word pass? No, it prints the word none. And now we'll see if we've passed the point of no return. We'll see what do we print. And it turns out that none evaluates to false. And so that's what we have here. None evaluates to false. So your methods will always return something, but that something could be none. What we really want, of course, is to use a return statement and then, use whatever's there. You'll also notice that this is equivalent. We can say return, and then it will also do that as well as pass. But I wanted the opportunity to show pass within this. So now we often hear people use methods and functions interchangeably because they're things that take input and give output, but they actually refer to two different things. So if we look up above here, if I have this a list, and I'll put 1, 2, and 3 within there, then len is a function. It takes as input there. We'll give it as 3. But ll.pop, that's a method. And what happened there? We popped the last value. We can pop the value in the 1th position as well, and that sort of thing. Now this is a method because it's a property of the list object class. So that's the language, the nomenclature that we would use here. So, if we go type ll, it should say type list. And if we go dir ll, that can show us these are all the methods: append, clear, copy. So there's not a huge number of methods for a list that we can use. Now, to say that a method is a property of an object, so the pop is a property of the list class, that means we probably have a sense that there's classes out there and somehow they're linked up. So we'll see those down below. And so we're going to create a class from scratch. Now, there only needs to be one method, a special method in every class, and it's called init. And it stands for initialize. So that means whenever you create an object of this class type, you initialize something. Now, you can initialize it with like literally nothing. Back to and so this might be where pass would be relevant. So if we do that, it's literally nothing, and we can see here we now have 2 pizzas with there's nothing in them. But on the other hand, what we really want to do is generally initialize an object that has some properties to it. And so in this case, the properties are going to be toppings, base, and sauce. So this will be, it's a pizza class. And so with our pizza class here, now we can create a pizza, and then we can create another pizza. These are 2 different instances of the pizza class. Now they're both going to have the classic base and the tomato sauce, but we can change them. And if we change one of them, if we change the P pizza here, it's not going to alter the Z pizza. And so you can see down here, we might do something like our toppings as a list. And we could have done it this way. Toppings equals this list, base equals classic, and this is just in a dictionary. But we don't do it that way. What would be the advantage of doing it with a class instead, a pizza object rather than a pizza as a dictionary? Oops. Pizza as a dictionary representing this stuff right here. Well, the idea is you get your own methods with it. That's, I guess, the most important one. The other one is that you get to set lots of defaults. So in this case, we set these defaults here, and you can just keep a lot more stuff in a class than you can just in this endless dictionary of data that might be nested in some obscure way. All right, so now down here, here's two approaches to printing off a receipt, so we can see those as a comparison. So we've switched from pizzas now down to receipts. So in this case, we have a cart. It's got items. It's got a code and a customer. So we can make our items. We can make that little turntable, microphone, and keyboard. Maybe I was buying music equipment or something when first writing this. So we could say our code was none, but now we're going to do it in cart customer equals Tom. So there we go. We have our cart, and it's got this stuff, and we can print this. It's a bit messy here, but just look at that. Welcome, Tom. Your items, and it's a turntable, microphone, keyboard, discount code, whatever. All right, so this gets the job done. So why would we bother with this complex cart thing? Well, if we want another object, making these dictionaries gets a bit clumsy after a while when we have consistent things we want to do. So now we have a cart class, and so first we'll initialize it. So it's the same thing. We have this init that we had up here, and I'll get to the self stuff now in a minute. I'll explain a little more about that, but let's start off with this right here. So we first initialize, and then we've got some items, a code, and a customer, and I've got a second function down here, or rather second method, called receipt. So now when we create an instance of a cart object, we can have a receipt as well as, I guess, just storing the items. And we can add other methods to this as well. So now just watch. I'll run that right there. It doesn't run. It's not up here. It did stuff, but up here we didn't get any output, and that's because we didn't create any instance of the cart class. So we can do that down here. You can see here, I've created a cart. And as for another convention, often objects, when you create an object, and you'll see that I've done this with most of my code, methods are lowercase, but objects are uppercase. And you'll see that elsewhere in all over in Python. So for example, in network analysis, we go import network x, and actually it's often convention to go import it as nx. So we'll say nx rather than network x. And if we want to create a network, like a social network or graph type of thing, we go, g equals nx dot graph. Or if we're using tables, like in spreadsheets, that would be pandas, and then pandas has pd, same thing. And that will be pd dot data frame. And again, it's in this uppercase. So that helps give you a clue as to what kind of the variables mean when people tend to work according to these conventions. Okay, so we've created a receipt here, and we've created a receipt up here. But now we have something much more flexible, because we can create a new receipt. We don't have to make our data any more complicated or duplicated. We can add new methods and so forth. Now let's see down here. For example, now we have a new receipt. We have y equals this kind of cart, y.items and y.customer. And so we can have the y receipt for the y cart, and then the x receipt for the x cart, which is what I created up here. And then I just put a little separator in there. So we can print the y receipt, then the x receipt. So you start to see how it's really kind of organizing your code together. The first way we organized it was through this function above, which groups together operations. But now imagine if you want to group together not just the operations, but also the objects that you're working on, and that's where we get a class. Now, before we go further, and it's in the writing, but it's kind of hard to read that writing when you're following along as I'm talking. So now I want to talk about the self before we go on. So classes, as you can, I guess, kind of visually see from the code, but you might have also guessed yourself, also have a notion of an inside and an outside. So whenever we initialize something, we're going to create a class or create an object from that class, and then there's going to be things that are inside the object and outside the object. Now, interestingly, you can access those things that are in the object from outside of it, but you have to do so with different naming conventions. So right down here, you'll see print x.receipt, and I put this in parentheses here because that's a method that we can run, and that's that method right there. But we can also work with this directly. You see, because we've created this cart right here, and I said, x.receipt, and that's the text right there. If we printed it, it would be nicely formatted. But we can actually directly access the items. So that's x.items or x.code, and then we can have y.code. So it looks like Chuck had a customer code and Katerina did not. But and so forth. So we can access the internal parts of an object should we need to, but it's better practice not to be accessing them directly if you can avoid it. Instead, it's better practice usually to use a method, and those methods are normally framed in terms of get and set. So you might get customer data or set customer data. Now that's not necessary, as you saw. We can edit that directly, but we don't. We tend to avoid that. But more importantly, down here I said y.customer or x.items, because that's the name of the object, and these are the properties of that object. So inside the cart class, that's what we have self for. That means that there are things that this object is going to have inside of it. There are, objects, stuff, and I want to be able to refer to those. So if I say self.items, that means every time we create an object, each object itself is going to have those items. And if we want to access those items inside of the class, we pass self along to it. So when we create a new method inside a class, we really should put self in there to say that you'll want to welcome in the objects of this class. If you don't, you could land in some trouble. It might give you an error. It might say it's expecting it. So whenever you create a new method in here, so let's say we say print MSG, and then I'll say self, and I'll go like so forth there. So now if I go down here, I've got my receipt, and I can go, x dot. And so you see, we didn't really pass anything else in there. We didn't need to. We just drew upon the methods that were in there. Now you notice that when I did this with y, it didn't work, but it did work with x. Any idea? Well, that's because what happened is that y is already an object. Y is already there, already has all the properties of the cart class as they were when y was instantiated, when we created an instance of y. It didn't have a print message in there at the time, so y is already in memory. It already has that stuff, so it doesn't know about this print statement. In order for us to use that print statement, we would have to create a new y instance. So let's say I run this again. It runs again, it looks exactly the same, but now y includes all the updated methods, so it should work. And there we go. Now you will find it a bit clumsy in here. See how I'm referring to self.customer, self.items. But I think it's if you just remember that self refers to what things are happening inside the method, then that should help guide you in this work here. Now sometimes you don't really want to reinvent the wheel. You don't want to totally write a new object, but the object that you want to work with doesn't necessarily have all of the things in there that you need. And so I give an example here from Twitter. This is of what's called extending a class. And so class extensions are what happen when you take an existing class and then you inherit all of the things that are in it. So imagine if we have an extension to the cart class, then it will inherit self.item, self.code, init, all this stuff there, unless we create a new init statement that somehow overwrites this, or a new receipt statement that overwrites this. Now, the use case for this was Twitter. So in Twitter, there's a class extension, or there's an expectation that you would take the method that it has inside of its Python code called stream listener, and then you would extend it. So you don't alter the stream listener, but you create an extension to it, perhaps called custom stream listener, and then you just add in the specified methods. And the reason it does that is because, let's say it's listening for tweets or X's or whatever they're called now coming in, then you'll want to do something with those, maybe store it in a database or parse the tweet or whatnot, and you write those inside your custom stream listener, because you don't mess with the stream listener class itself. And so, as I say here, one method that it'll look for is called onData. So that's when your listener, you're saying, like, if someone mentions, I don't know, me, I'll be waiting for a while, but if someone mentions, I don't know, Elon Musk or some character, then a new tweet comes in, a new X comes in, probably from Elon himself, and we'll get new data. So what we do with that data goes in our onData method inside our custom stream listener, and that's how we would work with live Twitter data. Now, we're not going to build a custom stream listener here. It's a wee bit more complicated, not just in the code. Actually, the code's not that hard. You just you'll do the example below and have the onData statement. Where it gets hard actually is in all the authentications, APIs, getting the keys, navigating that with Twitter, and that stuff is outside of the scope here. Instead, what I'm going to do is I'm going to create a trolley class. Now, you might have noticed I'm not from the UK, not originally, but I do live here now, and so over here they don't call them carts, they call them trolleys. And so what we're going to do is we're going to extend the cart class with some trolley specific things. So we have our init statement, and you notice that what we do here, we don't want to get rid of all the stuff that we initialized in the cart class. So I pass that in. I say cart init self. So observe what happens when you remove this. If you remove this, then it won't know about all these things up here. So we first initialize all of our variables for the cart, because it extends cart, so we want to make sure we're starting from that basis. And then I'm adding on a post code. This is not a postal code, as you might have somewhere else, but it's called postcodes. And here it is. This is the postcode for my current department where I work. It's the Oxford Internet Institute, right downtown in Oxford. And we also have another method here called delivery. Now, delivery will print something, but you'll notice that we're going to print and we're going to join self.items. We didn't initialize it directly because we already initialized it in cart.init. And then we have self.postcode, which we did initialize ourselves. Now, that's not going to be very exciting. It's not going to have a lot of stuff in there if we don't add items. But because we've extended the cart class, we can do all the things that we could with the cart class. So we're just going to add items in the way we did before, but now we'll get to have an extra method called delivery. So here we are. I have z.trolley, z.items, z.placename. Now, where does placename come from? Well, do we have a placename up here? We don't. As it turns out, you can add additional variables to a class. They don't have to come from the init statement. It's just that the init statement are the ones that you will get by default. But we can add more. Now, we don't use placename anywhere, so it's not really of consequence whether we have it or we don't. But the important thing here is to show that you're not restricted to what you put in the init statement. That's your defaults. Of course. Okay, so here we can see, and that's commented out, and says, welcome, here's your items, your basket currently includes will be delivered. So it ran this delivery thing right here. Now you'll also notice if I run this with the OII there, doesn't make a difference. It's happy that it has that, and in fact, it's Z, right? So Z, it'll say main.trolley, not cart. And if we go to items, like so forth, and if we go place name, and it has it as a property of that object, and that's not specific to carts or trolleys. That's, you can do that with pretty much any object in Python. Now you may find classes useful for your code. You may not find a need right away for you to create your own classes. You may think, I'll just get away with functions and so forth, and that's fine. But as your code scales and it gets more complex, you will want to bundle things up together, have a bunch of methods together with some related data and variables and so forth. And regardless of whether you do it or not, you'll almost certainly interact with other people who've done that. So as I, denoted above about the class name from Pandas, this is Pandas. This is the way in which we would do a lot of scientific calculations in Python. It's not the only way, but it's a really common way to manage tables. And so, of course, that means what we're doing is we're creating an instance. We're creating an instance of a data frame object, which itself is part of this Pandas library. So that's actually, this is a data frame class nested within a library, and we called it df here. So just look here, I've created an empty data frame with two columns, name and age. And then I said index range 5, so it's going to have 5 rows, but they're all empty. There's no data in there. And here we go. Here's an object. This is a data frame object, and the data frame object, unlike a list, it has tons of methods. There's lots and lots and lots of stuff we can do with the data frame object, and of course then we can even extend that, and other people have. So for example, there's a notion of a geodata frame, which is like this kind of thing, a table, except it has a column for geometry, and the geometry is what defines, I don't know if it's a point on a map, or if it's the shape of a province or a state or a country or an island or whatever. Those things go in the geometry. And it's the geographer people, they didn't have to create an entirely new data structure for Pandas. What they did is they extended this existing object here, this data frame object from Pandas. So that's kind of it really for the programming, for introducing Python, for the most Pythonic parts of this, or at least within JupyterLab. From here, you can really go on and start looking at all kinds of different packages, like I alluded to here, Pandas, and use them, knowing that they're objects that have methods, and they take in these things here. Remind, these are parameters, and these are arguments. So we have all of these within this. We can check what arguments it takes. You'll notice what we have are the default arguments here, and we can also see what sort of methods we can apply by going dir. So use that to navigate a whole series of different objects and structures within Python within your own work. And so it doesn't. The last chapter doesn't really expand our basic programming knowledge much, but it'll focus on how to get stuff out of Jupyter. But until then, I hope that you can make use of this code and do it to help make your programs more scalable, more robust, not just one operation after another, but seeing the commonalities in these operations and then being able to factor those out, put them in their own place, and reference them as you need to. So hopefully you'll make use of that and enjoy it, and I thank you for watching.